Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and in today's short application exercise, we'll program and test a PLC-based unidirectional motor starter with both a momentary jogging operation and a maintained run state. This lecture is predicated on the assumption the viewers watched the Commissioning a PLC System featuring the TECO SG2 PLR lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. This aforementioned lecture configured a TECO SG2 PLR, an inexpensive basic PLC, to direct the operation of light industrial 120 volts line to neutral, 208 volts line to line, 60 Hz three-phase AC primary circuit, configured such that the F contactor energizes a squirrel cage induction motor in the forward direction, and the R contactor energizes a squirrel cage induction motor in the reverse direction. The F and R contactors are mechanically interlocked such that they cannot be simultaneously closed. The PLC has been configured with the following field input and output devices: a normally opened maintain contact selector switch on input 1, a normally closed momentary contact red push button on input 2, a normally open momentary contact green push button on input 3, a normally open momentary contact yellow push button on input 4, the normally open auxiliary F1 contact of the F contactor on input 5, and the normally open R1 auxiliary contact of the R contactor on input 6. The first 4 field input devices are intended for human-initiated interaction with our system, whereas the auxiliary contacts on inputs 5 and 6 serve as feedback about the status of a particular contactor. Note the maintain contact normally closed e-stop is not a direct input to the PLC, but rather serves as a hardwired bottleneck through which all 6 field input devices immediately downstream of it must negotiate to issue input to the PLC. Wired in this fashion, the hardwired e-stop effectively severs all incoming communication with the outside world without the necessity of resorting to any programmed instructions to do so. Let's now examine the field output devices. Electromechanical relay output Q1 directs the operation of the F contactor coil, hardwired with a normally closed overload contact. Electromechanical relay output Q2 directs the operation of the R contactor coil, also hardwired with the same normally closed overload contact. This hardwired connection between the 2 contactor coils and the normally closed set of overload contacts allows the overload to have the last say as to whether the motor is energized or not, and never surrenders complete authority to the PLC. Wired in this fashion, the normally closed overload serves as a means of directly de-energizing either contactor coil in the event of an overload without the necessity of resorting to any programmed instructions to do so. Electromechanical relay output Q3 directs the operation of a red pilot lamp, and electromechanical relay output Q4 directs the operation of a green pilot lamp. Again, note the maintain contact normally closed e-stop serves as a hardwired bottleneck through which all field output devices immediately downstream of it must negotiate to be energized. Wired in this fashion, the hardwired e-stop directly above stream of all field output devices effectively severs all outgoing communication from the PLC without the necessity of resorting to any programmed instructions to do so. For the purposes of this exercise, we will not be making use of all field input and output devices. However, this base system is configured as such for other exercises that may need this additional functionality. Given this PLC can be quickly programmed and reprogrammed as we see fit without the time-consuming necessity of physically rewiring it, this and the next several labs making use of this system should be relatively quick and painless. Here's the pared down schematic representing all of those field input and output devices and primary elements we'll be making use of today. You will no doubt recall that a through-wire control circuit maintains or remembers the last asserted state because it features a holding, seal-in, or memory circuit. A jogging or inching circuit, in contrast, is one that only momentarily energizes an output without the use of a holding circuit. A jogging circuit could be used to briefly energize a motor for purposes of partial movement of an applied load. Customarily, jogging circuits feature spring-applied electrically released friction brakes to increase the precision of the jogging movement. If you necessitate a review of jogging circuits as implemented using traditional hardwire relay-based ladder logic, you are encouraged to revisit the Motor Starters with Jogging lecture available at the Big Bad Tech channel. Various configurations of jogging circuits exist. However, here's the hardwired equivalent we'll attempt to replicate today using the PLC. I chose this particular jogging circuit for today's activity solely because it's not as easy as one might think to implement using a PLC. You might wish to pause the lecture and review how this hardwired implementation might behave given various combinations of input, particularly when an operator presses and releases run, then presses and releases stop. When an operator presses, briefly holds, then releases jog stop. When an operator presses and releases run, then presses, briefly holds, and releases jog stop, and finally, its response to emergency stops, overload conditions, and occasions when the F contactor is physically forced closed. I say again, pause the lecture and familiarize yourself with the function of this hardwired jogging circuit as implemented using traditional hardwire relay-based ladder logic. Dust the cobwebs off that part of your brain where you stored jogging circuits long ago and get to work. Again, if you need help, please revisit the Motor Starters with Jogging lecture available at the Big Bad Tech channel. Assuming you were up to the task, you should have anticipated the following behavior. When an operator presses and releases run, the motor should start, continue to run, since control relay CR1 and its associated contacts establish a holding circuit. When an operator presses and releases stop, the motor should stop and stay stopped since the holding circuit is broken. When an operator presses, briefly holds, then releases jog stop, the motor should run only when the jog stop button is actively being depressed, and upon release, the motor should stop given the holding circuit has not been established by control relay CR1 and its associated contacts. When an operator presses and releases run, the motor should start and continue to run since control relay CR1 and its associated contacts establish a holding circuit. While in the maintain run state, when an operator presses, briefly holds, and releases jog stop, the motor should continue to run only when the jog stop button is actively being depressed, and upon release, the motor should stop given the holding circuit established by control relay CR1 and its associated contacts has been broken by the normally closed side of the mechanically interlocked jog stop button. Really, the only distinction between the maintain run state and the momentary jog mode is whether or not the control relay CR1 is energized. In the maintain run state, CR1 is energized and establishes the holding circuit. In the momentary jog mode, the normally closed side of the jog stop button ensures CR1 is not energized and breaks or does not establish the holding circuit. At the same time, the normally open side of the jog stop button energizes the F contactor coil directly. The moment the jog stop button is released, the motor stops. Again, the accuracy of the jogging movement can be increased by incorporating a friction brake in our primary circuit. During an emergency stop, this system will stop the motor and break the holding circuit regardless of whatever state it happens to be at the time. The system will only return to operation when the e-stop is reset. Similarly, during an overload, this system will stop the motor and break the holding circuit regardless of whatever state it happens to be in at the time. This system will only return to operation when the overload is cooled and reset. Finally, if the F contactor is physically forced closed, note the primary F contacts will make connection and the motor will start. However, the F contactor coil will not be energized, nor will the holding circuit be established. As such, when a technician stops manually overriding the F contactor, the motor will stop. Ideally, we should be able to replicate the functionality of this hardwired implementation using our PLC-based system. Easy, right? No, but not impossible, as we'll soon demonstrate. If you've been following this playlist in its intended sequence, you're most likely sick, and no doubt tired of hearing about all the wondrous benefits of PLCs, as I am tired of going on and on and on about them. Put your hand on top of the internet and repeat after me. PLCs are flexible, reprogrammable devices that make modifications of a system possible without the time-consuming necessity of physically rewiring it. I too share this belief. However, PLCs are not without their shortcomings and idiosyncrasies, as I intend to demonstrate today. Often these shortcomings and idiosyncrasies necessitate creative thinking and a shift in perspective to circumvent. First obstacle to our task is that the PLC chosen for this exercise, the TECO SG2 PLR, is limited to a maximum of only 3 available contacts and 1 output entry per rung. Given this limitation, we're effectively being asked to stuff a watermelon inside a lemon, given the first rung of our hardwired equivalent contains no less than 6 elements. Our task is somewhat simplified, however, by having the e-stop and overload already being hardwired into this system. However, we're still constrained by the available space. Add to our difficulties that our PLC-based implementation needs to effectively respond to overload conditions using real-world feedback using the F1 auxiliary contact, and the fact that we don't want this system to energize the F contactor coil and establish a holding circuit if the F contactor is ever physically forced closed. One might propose the following program, almost a direct copy of the hardwired implementation, only to have our dreams shattered into so many tiny pieces because it violates the space limitations of the TECO SG2 PLR. Note this implementation requires the use of 4 contact entries, in clear violation of the 4 contact entry limit per rung. This being said, it's close and worthy of our inspection. If this program works as intended, we may be able to chop its arms and legs off, roll it up and stuff it in a small box and stomp the lid closed if we get creative and/or desperate. For the purpose of this exercise, we're going to use the normally closed momentary contact red push button on input 2 as our stop button, the normally open momentary contact green push button on input 3 as our maintain run button, the normally open momentary contact yellow push button on input 4 is our jog stop button, and the normally open F1 auxiliary contact of the F contactor on input 5 as feedback input. Note Rung 1 contains a make instruction examining input I2, the normally closed momentary contact red stop push button, a make instruction examining input I3, the normally open momentary contact green run push button, and a break instruction examining input I4, the normally open momentary contact yellow jog stop push button in series with a coil of virtual relay M1. Rung 1 appears almost identical to our hardwired implementation, with a notable exception that virtual relay M1, our stand-in for control relay CR1, is not a real physical entity, but rather a programmed virtual element. Rung 2 is where the PLC program departs from our hardwired implementation out of functional necessity. Rung 2 contains the make instruction examining virtual relay M1 and the make instruction examining input I5, the F1 auxiliary contact, in parallel with the make instruction examining I3 in Rung 1. This rung establishes the holding circuit if and only if both the coil of virtual relay M1 is energized and the F1 auxiliary contact confirms the F contactor is actually closed. If either scenario is untrue, either because the system is at rest and someone is forcing the F contactor closed, or while the system is running in an overload event directly de-energize the F contactor coil, the holding circuit will not be established, or if previously established, will be broken. The third and final implementation of the PLC-based 3-wire motor starter lecture, available at the Big Bad Tech channel, discusses this modification in greater detail if you wish to review it. Rungs 3 and 4 are again almost direct one-for-one translations of our existing hardwired implementation. Either the make instruction examining input I4, the normally open momentary contact yellow jog stop push button, or the make instruction examining virtual relay M1 would serve to energize output Q1, the F contactor coil. Again, you'll note neither the e-stop nor the normally closed overload make an appearance in our program. However, these devices are readily apparent in the hardwire schematic. Wired in this fashion, the e-stop and the normally closed overload would serve to override the PLC program in the event of an emergency overload event. This implementation would work if we used an even slightly more advanced PLC that allowed more contact entries per rung. However, we're stuck using the tools we've got on hand, notably a PLC that allows only 3 contact entries per rung. Given this limitation, we need to modify the circuit ever so slightly to accommodate this restriction.